Let's consider two objects. Let's say they're two blocks that are moving along and they collide with each other. So for that to happen, let's say that this one is moving that fast and this one is moving that fast. And so I'm going to call this A and B. Therefore, this would be VA. This would be VB. Okay. And then this one's obviously going to catch up to that one, and then they'll bump into each other. They'll collide. And the question is, well, what happens afterwards? Well, part of it depends on how they collide. And there's two general types of collisions we're going to talk about. One is called inelastic collisions, and that's what I'm going to focus on in this video. An inelastic collision says that after they collide, so this is before they collide, and this will be after they collide. An inelastic collision is when they stick together. So here's A, here's B, that are now moving as one object with some speed. I could call that just V final. Okay, which means that I need to be careful to label these as initials, or maybe I'll use ones and zeros and ones. But the thing is the velocities in the initial case are different. They're dependent on the individual blocks. But in the final case, an inelastic collision is defined as having a common final velocity. So there's no V final A or V final B. It's just V final of the object. This is moving like one object with a mass of A plus B, okay, and moving with this common final velocity. All right. Now we can use our general conservation of momentum to analyze this problem, but this is such a ubiquitous problem. It happens in so many different scenarios in life that it's good to focus our attention on it. And so let's go ahead and try and figure out how would we analyze this. We have conservation of momentum, which would say that P final equals P initial if we're talking about our whole system. Okay. Oops, sorry, I put an F. P. Sorry about that. So we have our final momentum must equal our initial momentum for the whole system. Okay, or I could reverse it. Now this is assuming that there's no significant external forces. All right, and I'm going to build on that in just a second. Okay, but let's go ahead and look. Let's just pull out. Okay, well, we'll choose. I'm going to choose to the right to be positive, just to keep things consistent. And so in our final case, we have this object moving later, but I'm going to have M A plus B times this B final is going to equal, and in my initial case, I have two separate things. So I'm going to have MA times VA initial plus MB times VB initial. And they're all in the same direction, so they all have the same signs. Okay, now, but if this one was moving backwards, then I would have a minus sign on B. Okay, and and it doesn't, so this, sorry, I'm stuttering. This, whatever directions, this will work as long as you define a proper positive direction. Okay, so I could have this one moving that way and this one moving that way, increasing, doesn't really matter. Okay, but an important thing is that we may not even know the direction of this, because if this one was moving backwards and this one is moving forward, well, this one could be moving backwards. We don't know. And it's all right, because if I choose a direction, say this is positive, and I end up with a minus sign, well, guess what? I just made the incorrect guess, but my answer tells me what the correct guess is. So we don't need to really worry about the unknown direction. If we can't guess it from the physical situation, then we just choose to be positive and then see if we end up with a positive or a negative value when we're done. Okay, so this is the way we can compare these velocities. Now I want to point out one little thing here, is what if we had this, actually these boxes were sliding on a surface, okay? Let's say that surface, there was some friction, so it was not a frictionless surface. Well, as these are sliding, when they're far apart, well, this will slow down and this will slow down. So if the question is, could I still apply this? Well, if we remember when we consider momentum, that if we consider right before and right after the collision, that means that the delta t is crazy small. And if you remember, we were able to say initial equals final here because delta p of our system was equal to the impulse, or the integral of f dt, okay, from some initial time to some final time. And this would be external forces, not internal. There's internal forces between these two objects, but external forces. And so if there are no external forces, then final the delta is 0, so final equals initial. But if there are forces, but over a very small time interval, this is very small. And so during a collision, collisions usually happen crazy fast. You know, when you bounce a ball, how much time is the ball actually in contact with the ground? And so if I start my process considering the velocities right before they collide, and then consider the velocities right after they collide, then the delta t is crazy small, and I can use conservation of momentum. I don't care if there's friction in the problem. I don't care if there's gravity in the problem, because the time is too small for them to have an effect over that small time interval. That effect is super small compared to the massive forces of the collision itself. So in thinking about doing collisions, you have to remember we're analyzing right before and right after the collision.